Okay, so our next speaker is Jessica Martinez, and she is going to talk about machine learning, the 2RD. Okay.
Thank you so much for the introduction. Then I will start from the quantum many-value problem. I'm going to start from the beginning. This relies on the solution of the Schrödinger equation, in which we have an electron Hamiltonian that contains the kinetic energy of the electrons, electronuclear attraction, and electron repulsion. In principle, this can be solved exactly in order to form the grand state function. However, all we know that we need to account for the simultaneous interaction of all of the electrons in our system. Therefore, we cannot solve it. But we rely on approximations. The first and the most simple approximation is the Hartree-Fock method, in which we use a symbol that we determine in order, or using the variational principle or ansatz, then we can find a non-correlated solution for our ground state. If we increase the complexity of this wave function by using single reference or multi-reference wave function methods, we are going to this missing correlation from Hartree-Fock. However, these methods start to scaling into the 4, into the 6, even combinatorially or exponentially, making it so complicated to apply for molecular systems that are big in number of atoms. Therefore, as we have seen here, density functional theory becomes the method of choice in order to study big molecular systems by focusing on the electron density instead of the full interacting wave function, right? However, we have one scalar n to the qubit, and also we don't have a final answer for the chain coordination function. Therefore, here, just coming back from machine learning can be seen as a possible solution in 2 different ways. First, we have models that start from molecular structure feature that taking huge data sets. Or we can think machine learning as an integrated or subrogated ab initio technique. Then here, based on the principle of quantum mechanics, I will teach you, or I will tell you about how to learn the 2-value values and RDM. Okay, then we start from the second quantization, in which our electron Hamiltonian is divided in the 1 electron operator and the 2 electron operator, right? We can build this K matrix by add the corresponding delta chronicle, so that the energy functional becomes linear, okay, or is linear. Thus, we have a direct access to the total energy. Simple as that. But as we want to get a subrogated machine learning technique that it adds directly the total energy, that's why we are not here going to focus in the 1 RDM or the electron density, because we still don't have a final answer for the energy functional based on 1 RDM, either the electron density. Therefore, then we are going to explore the fundamental bijective maps. Then, as we started early, we can have bijective maps between the external potential and the density, but as we want to build a machine learning technique, we should add an extra machine learning step, the so-called delta learning that was Carlos mentioned this morning, in order to obtain the either where it is in density or the 1 RDM. Therefore, by experimenting the 2 RDM, we can avoid this mapping and directly do the mapping between the external potential and the 2 variable density maps. This will allow us to have direct access to the energy. Then coming back, we are going to use the same concept, kernel plus regression, in which gamma 2 will become functional of the external potential, so that for a given kernel, we can find, hopefully, an irrepresentable probability. Okay.
Tell me something. In 2 RDM functional theory, is this one-to-one correspondence exactly proven?
It is.
Is the? I seem to remember that the n representability is a problem there. So the proof is. You're talking about this now. Okay, all right.
But that is important.
Okay.
But not in a formal way. But
yeah, I remember seeing these papers by Manciotti et al., who's been working on this stuff for whatever 20 years, and there's always, these nice things. If you know the gamma 2, you know everything, right? But how do you get, well, how do you get
Exactly.
it? Like, is it even, are you even allowed to do this? Is this thing even?
This is something we never thought about it before. But
Was it-
We'll assume that that map exists.
So don't ask, don't tell.
Don't ask.
Yeah.
But should ask.
but it's important to mention that no, it's okay. That here, as I mentioned before, we need to be sure that we have an unrepresentable tour again, as mentioned in this paper. How we're gonna do that, I'm gonna show you. Here we have the predicted gamma 2. We are going to contract it to the corresponding gamma 1 because the gamma 2 has all the information, including the gamma 1. And here we're going to apply something that we call the purification, which is basically impose the occupation numbers to follow an invertible distribution. In this case, this invertible distribution is a Fermi-Dirac distribution. Okay, this we are going to start here. But we are going to rely in the unitary decomposition. This unitary decomposition allowed us to split the gamma 2 in 3 different parts. The gamma 0, which relies only on information of the one RDM, of the one RDM, the construction from the one RDM, the gamma 1, and the gamma 2. The gamma 2 will contain all the information that cannot be constructed from the information of the gamma 1. There is a way, okay. Therefore, this gamma 2 part, we are not going to touch it. We rely on the good prediction of our model. But the portions that, the portions that relies on the information of the gamma 1, if you can see it here, we are going to replace it for this purified gamma 1. Here, in this case, the gamma 1 is the one that relies on the gamma, the capital gamma 1 is the one that relies on the gamma 1. That's important to mention.
So you're assuming gamma 2 is small.
Yes.
You can neglect it.
No, we are not neglected. We are going to keep it. This portion from the model, the predicted gamma 2 from the model. And then, we have the full gamma. We have this predicted. We have 3 parts. The first one, the gamma 2, we are going to keep it as it is. But we are going to replace the portion that depends on the gamma 1 with this purified gamma.
You mean one at the end?
The one at the end. Yeah.
The gamma 1 is gamma 1.
Yeah, sorry. The one at the end. Then as we replace it here, we are going to purify only the portion that depends directly on the one at the end. And then the gamma 0, which keep only the trace information. Then we can replace it exactly for what is the trace of gamma 2 with n minus.
It's not a full purification, but
that's why we said it is a partial in representability in which we need to satisfy the D, G, and Q conditions. D conditions be the particle G, be the particle whole, and Q whole focal. I just do.
So I just wanted to ask real quick, you have trace prime there, so which states are you taking the trace over?
on the top left.
This
Top
one?
left.
The top left. Yeah.
Top left. Oh, this guy?
Yeah, the trace prime.
Okay, yeah, because this trace is not the full trace. If we have to do a special trace to take the elements just to be the second less 2 elements. Like if you have PQ and S, you make PQ and F. This is your trace over the segment.
I see. Okay.
Yeah, that's important. It's on a special trace. Then, therefore, here I'm gonna tell you how we are doing and how we're building this machine. Then first, we're gonna take a set of molecular geometries, same way as we did for the one at the end. It's a vibrational normal mode sampling. For here, we take an external potential. As the gamma 2, as I mentioned before, has a lot of information, we can take 2 ways. Either way, by learning the correlated gamma. The correlated gamma is defined as the difference of the full gamma minus the wedge product of a non-interacting gamma 1, which means the Hartree-Fock 1 RDM. This is the called gamma Hartree-Fock. Then we reveal the gamma at the cost of a Hartree-Fock calculation. Then at the end, our gamma, full gamma 2, will be the gamma 2 Hartree-Fock plus the correlated machine learned gamma. The second way is by learning the cumulant gamma 2. The cumulant gamma 2 is defined confirm, is defined as the full gamma minus the wash product of a correlated one body by density matrix. You can confirm here. Then at the end, we are going to have a gamma 2, which is bit from the gamma A prime, which is bitted from the correlated gamma 1 and the cumulant machine learning, at the cost of having a gamma 1 coming from the machine learning model. Then with this, we can either apply purification or not. It's not that always we need to purify it, and how good our machine learning model is to get high quality 2 RDMs and 1 RDMs. In principle, we can get potential energy surfaces, aviation molecular dynamics, and also X-ray scattering power. All of this is implemented in a code called QLearn. You can go in. Okay, the first of all, here they have the potential energy surface along the dissociation bond between the hydrogen and oxygen of a single water molecule. You can see here the full CI line. Either learning the cumulant or the correlated gamma 2 give us a really good results for the total energy. However, if we learn the full gamma, you can see that we have high divergence in the extrapolation regimes. These extrapolation regimes are the ones that are outside of this blue history. This is by using a linear kernel. If we use an RDF kernel, we have similar results. We are really good doing also an extrapolation capacity for the gamma.
What does RDF stand for again?
Radial basis functional, which is basically a Gaussian type kernel. Now, here is the purification effect. Okay, now we are going to focus only in the correlated gamma. I have here the results for the linear kernel. If you see no purify here is the purple line. We are a little bit farther from the full CI reference. However, if we apply purification, the purification I showed you at the beginning, we are closer to the corresponding full CI. It means our purification is giving a good effect in order to get an representable 2 RDM. If you take a look now in the RBF, the predicted RBF is already good. Then we don't need purification at all. But then you may ask, is just because it follows the energy profile is good? No, we need to check the representability conditions. How we can do that? We take the lowest eigenvalue of our corresponding gamma, the D, G, and Q. If you take a look, the RBF kernel gives us already the lowest positive value for this solution, which means our gamma 2 is in representability and the RBF model is much better than the linear, as we say. Okay, come on. Now, we also can do aviation molecular dynamics by taking the gradient of the forces with respect to the Hartree fold, the Ka matrix, and the corresponding gamma. If you take a look here, in orange is the CCSD reference value. And if we run this for a lot of 8 picoseconds, we have an stable MD. If we compare this from the learning of gamma, one body per density matrix, using delta learning, you can see that it, after 1 picoseconds, starts to drift. Okay, it doesn't mean that the 1 RDM is a bad model. It means that we need more number of points in order to get a better machine learning model. But here, as we rely in the Hartree fold calculation, we have more stable and we need less number of points in order to do our machine learning. This is even more visible if we increase the temperature. We go now to 400 Kelvin and we train at 300 Kelvin. You can see that also we have a really good stable MD for the ammonia molecule for the tometry.
Okay.
Okay,
sorry, can you sort of just
say
again what the difference between the blue and the green was? One of them is a little gamma. I forget now.
Yeah. The one at the end, it was this morning of the learning of the one at the end, this morning early morning. Here we have external gamma and then delta learning, which is gamma directly to the energy and to the forces. With that, here the difference with our model is that we use directly the gamma 2 and we take the gradients to get the forces. There's two different ways to make it.
So the green one is from the one at the end.
Exactly, just the T1 RDM.
Train at 300 Kelvin with 216 points in your training
It's
set.
training set, exactly. As you expected, as this was trained at 300 Kelvin, the energies will vary at 400, right? Then therefore, they will drift much faster than the corresponding to RDM. As the to RDM relies also on the Hartree-Fock calculation, it really doesn't matter the temperature because we keep like the electronic structure base.
Well, it's obvious you have to do the blue one.
Yes. One asks why is the blue one so stable, and like she says, because hey, for the 2RDM we are using a Hartree-Fock calculation first, which gets the biggest part of the 2RDM, and then we're doing machine learning for a small part, and that's it's good enough.
Yeah, I think essentially if you do like gamma 1 RDM in the same fashion where you
it would still be fine.
yeah, it
Yes.
will still be fine. Yeah.
Okay, we also do X-ray scattering factors, which is basically the total scattering will depend on the Fourier transform of the per electron density that comes from the 2RDM, and then if we make this transformation, we can get the total X-ray scattering factor. If we not take the Fourier transform of the 1RDM or electron density, well, get the electron density, we can get the elastic related scattering. If we make the difference, we get the inelastic content scattering. Right? With our predicted gamma 2 and gamma 1, we obtain the experiment results that start from the n squared, when n is the total number of atoms for the water molecules, and we basically are on top of the using our machine learning method for all of the three components. Okay, I forgot to mention that we do this analysis for the vibration displays, the displacements along the vibrational modes. Then the blue line, the darker blue line, will be the more stable geometry. As soon as you go more displaced, then you can see this broader blue here. Okay, but here the important question is, as we are predicting the correlated, how good the correlated part is. Then here you have the total, you have the correlated ML, and you have the correlated CCSD as our reference. You can see that we are really good on getting this portion. Last but not least, we also, well, we are still testing this. We are going to get the rotation energy values along the ethylene angle, the dihedral angle that will start in this 0 dihedral, and then when it achieves 90, we have a difference in geometry and in symmetry, and therefore capture these two, the mixing of these two states when you have 90 degrees is really complicated. But we wish that our machine learning model can learn these two RDMs along this dihedral rotation. Then you can see here, I have the dihedral difference, 0 being, okay, forgot to mention. We start with points that are outside of the training. The training are these 45, each 45 dihedral angle. And then if we start with geometries outside of this training set, we achieve the convergence to the more stable, which it means the planar geometry for the ethylene. Then it is working, it needs 2,700 points. This is linear, kernel steel. We're still testing this because as soon as we increase the CAS, it becomes a little bit more complicated.
This is hard because there is a double bond.
Yeah, oh, yeah.
To carbon.
So
when you twist,
okay, this species, okay. You have a double bond for the ethylene, then you have a p orbitals. Then these p orbitals are lobster here, up and down. Then as soon as you torsion these orbitals start to overlap. Then they're gonna mix up a state for the ground state, even with the triplet states, which makes it so hard to learn because we also have to take into account excited as our transition density matrices for these constructs. Then saying this, here I will just show you the timings for a single water molecule. We have Hartree-Fock timing calculation, and all of this is post-Hartree-Fock cost. If you see full CI, and you see the full CI machine learning, even using linear, or RPF is much cheaper than full CI, but we are getting a full CI molecule. Here I'm showing how good our machine learning is. Then as a conclusion, then we showed that learning only the correlated of the cumulant part gives superior extrapolation accuracy. The partial purification improved energy predictions. Our model based on the gamma C get stable and energy conserving ignition molecular dynamics. The RDF kernel generally offered better accuracy and fulfilled positivity conditions. X-ray scattering intensities reproduce the experiment and the ignition reference, and our machine learning model can effectively predict blue RDM even during character change. Then I will say thank you to all my group, all the members, past and new members of my group, and you for your attention.